as opposed to simple harmonic motion produced by a spring or planetary motion, which are unconstrained motions. In the case of constrained motions, objects move along fixed curves or surfaces. For example, while a body moves along a curved track or slides on a table or a slope, it has to stay in contact with the surface of the track, the table or the slope. In such a situation, the body is forced to move in a restricted way, that is, restrictions are imposed on the motion or position or both of a body, which are known as the constraints limiting its motion. Mathematically, constraints are given by the equations describing the geometric elements restricting the motion of the point-like bodies. These geometric elements are normally curves and surfaces, and the equations describing them can be constructed by applying a coordinate system adapted to the trajectory of the constrained motion. In the case of a ball rolling on the floor, the constraint imposed on the motion of the ball tells us that the ball can only move in the horizontal plane determined by the floor. If the ball is rolling down a ramp, then the constraint restricts its motion along the surface of the ramp. For the horizontal motion, we can attach a Cartesian coordinate system to the floor considered as a frame of reference such that its x-axis oriented along the surface of the floor, and its y-axis is perpendicular to this surface. For the motion on the ramp, we can orient the x-axis of the Cartesian coordinate system along the surface of the ramp, while its y-axis is perpendicular to the surface. Then the constraint for the moving ball is described by the equation stating that the coordinate y of the position of the center of the ball is constant during its motion in both cases. If we consider the ball as a point mass, then we can state that the y-coordinate of the position of the moving ball remains 0. For the circular motion of a point mass m, the frame of reference is attached to the center O of the trajectory of a point-like body, which can be chosen as the center of a polar coordinate system with an x-axis pointing in an arbitrary direction in the plane of the motion. Here the distance of the point mass from the center O is given by the radial coordinate r, while the azimuthal angle phi describes the instantaneous position of the body on its trajectory. A simple pendulum, which consists of a point mass m hanging from the string attached to the pivot point O, also performs a constrained motion. The pivot point O can be chosen as both the reference point of the motion and the origin of the polar coordinate system, where the x-axis points downward. The radial coordinate r of the point mass is equal to the length of the string, while the azimuthal angle phi describes the instantaneous position of the body on its trajectory. In both cases, the constraint of the motion is given by the equations stating that the radial coordinate r describing the distance of the body from the point O is constant during the motion. The role of constraints is not only evident for moving objects, but constraints can also be applied in the description of bodies at rest where the forces acting on the body are in balance. For example, if a body is at rest on the table, then the weight g of the body pushes the table. The principle of the action and reaction states that the force minus g is exerted on the body by the table due to the deformation of the surface of the table. Although the deformation is very small, the force minus g produced by this deformation is obviously a force acting on the body. Therefore, the gravitational force g acting on the body is an unconstrained force, whereas the reaction minus g describes the effect of the constraint imposed by the surface of the table, and it is called constraint force. The net force F acting on the body vanishes, that is, F is equal to the action g plus the reaction minus g, which is equal to 0. As a result, the forces acting on the body are in balance and the body stays at rest. We already interpreted this force balance by stating that the table prevents the body from falling down, but we can also consider the body as a point mass under the influence of the net force F, which is equal to 0. Based on this example, we can see that the fundamental equation of dynamics has the following form for the constrained motion of a point mass m. The mass m times the acceleration a of the point mass is equal to the net force F acting on the body, which is given by the sum of the net force F0 of the unconstrained forces exerted on the body and the net force F' of constrained forces exerted on the body. Such a decomposition of the net force F is justified by the fact that the unconstrained forces acting on a body, such as weight, gravitational force, quasi-elastic force or the force of air resistance, are generally known from the laws of force, as opposed to the constrained forces acting on the body. It is the part of the tasks to determine the constrained forces in the system under study. Nevertheless, constrained forces can easily be determined from the constraints and the law of action and reaction in simple cases, since such forces are usually perpendicular to the given surfaces or curves representing the constraints. Let us illustrate these statements with some examples. In the first example, let us consider the forces acting on a body which is on a ramp with the angle alpha measured between the horizontal plane and the surface of the ramp. The weight g of the body is equal to the mass m of the body times the gravitational acceleration g, which points downward. We can decompose this force to the component Gn normal to the surface of the slope, and the component Gt tangent to the surface. That is, the weight G of the body is equal to the vector sum of the components Gn and Gt, as the parallelogram law applied for these forces shows in the figure. Then the magnitude of the normal component is given by the mass m times the magnitude of the gravitational acceleration g times cosine alpha, and the magnitude of the tangential component is equal to m times g times sine alpha. Since we neglect the friction between the body and the surface of the ramp, the tangential force Gt does not act on the ramp. However, the normal component Gn is exerted on the ramp, and as a reaction, the constrained force F' due to the deformation of its surface is also exerted on the body, where F' is equal to minus Gn. As a result, both the unconstrained force F0 given by the weight G, that is the gravitational force, and the constrained force F' act on the body. Then the net force F exerted on the body is equal to the sum of F0 and F', that is the weight G minus the normal component Gn. Since the weight G is decomposed to its normal and tangential components, the result is given by the tangential component Gt of the weight. That is, the net force F acting on the body points in the tangential direction and its magnitude is equal to the mass m times the magnitude of the gravitational acceleration g, times sine alpha. The fundamental equation of dynamics states that the force F exerted on the body is equal to its mass m times its acceleration a. By applying this equation, we can demonstrate that the body slides down the ramp, and its acceleration a is equal to the tangential component gt acting on the body, divided by its mass m. Then the acceleration of the body has also a tangential direction, and its magnitude is equal to the magnitude of the gravitational acceleration g, times sine alpha. This formula shows that the steeper the ramp is, the greater the acceleration of the body is. In a limiting case where alpha tends to 90 degrees, the acceleration of the body approaches the gravitational acceleration g, and we can talk about the free fall of the body along a vertical surface. For alpha equal to 0, the ramp becomes a horizontal surface and the body has no acceleration. Therefore, if the body was already at rest, then it stays at rest. If we perform the experiment, then we always measure smaller values for the magnitude of the acceleration of the body than g times sine alpha. Since the frictionless motion is an idealized model, the friction between a sliding body and the surface of the ramp reduces the magnitude of the acceleration of the body. Similarly, since bodies have extension and shape, in the case of rolling balls, the rotation of the ball also reduces the magnitude of its acceleration. However, the acceleration is still constant in both cases, and the body moving on a ramp performs a uniformly accelerating motion. As a result, the distance s covered by the body sliding on or rolling down the ramp under the influence of gravity is given by 1/2 times the magnitude of the acceleration a of the body, times the square of the time t measured during its motion. In other words, the distance s between the initial and the final positions of the body is directly proportional to the square of the elapsed time t. This fact was demonstrated by Galileo in his inclined plane experiment, as we discussed it in kinematics. We can also compensate the force Gt acting on the body in a setup, or we connect a cart to a weight with a string over a pulley and place it on a ramp, as seen in the figure. If the inclination angle alpha of the ramp can be adjusted, we can find an angle where the cart and the weight remain at rest. Then the tangential force Gt acting on the cart and the force minus Gt exerted on the cart by the string are in balance. Similarly, the force G' acting on the weight under the influence of gravity and the force minus G' exerted on the weight by the string are also in balance. In such a configuration, the magnitudes of the forces minus Gt and minus G' are equal, and given by the mass m of the cart times the magnitude of the gravitational acceleration g times sine alpha. This relationship shows that the inclination angle alpha of the ramp is uniquely determined by the mass m of the cart and the weight G'. In the next experiment, we connect a cart to a spring dynamometer or a spring scale with a string and place it on a table. We connect the other end of the scale to a weight with a string over a fixed pulley attached to the table, and suspend the weight from the spring, as seen in the figure. Let M1 and M2 denote the mass of the weight and the cart respectively. Then the weight G1 is given by the mass M1 times the gravitational acceleration g, and the weight G2 of the cart is equal to the mass M2 times the gravitational acceleration g. In this setup, the cart is held in the same position on the table so that the whole system is at rest. If the mass of the spring scale is much smaller than the total mass of the weight in the cart, the magnitude of the force F' exerted on the cart by the string is equal to the magnitude of the weight G1. Then the magnitude of the force F' is equal to the mass M1 of the weight times the magnitude of the gravitational acceleration g, which is measured by the spring scale. If we let the cart move, then it performs a uniformly accelerating motion, that is, the distance covered by the moving cart is directly proportional to the square of the time t measured from the beginning of its motion. In the moving system, the spring scale measures a force less than the mass m1 times the magnitude of the gravitational acceleration g. If the unconstrained forces g1 and g2 are known, we can determine both the motion of the bodies and the forces acting on them. The weight g2 of the cart is a force exerted on the table which we consider as action, and the reaction minus g2 is exerted on the cart by the table. These forces compensate each other, and they do not accelerate the cart. The forces F' and minus g1 pulling the strings and the spring scale point to left and upward respectively, but they have the same magnitude. As a result, the magnitude of the net force acting on the weight is given by the mass m1 times the magnitude of the gravitational acceleration g, minus the magnitude of the force F', whereas the magnitude of the net force acting on the cart is equal to the magnitude of the force F'. If we suppose that the strained strings cannot be stretched, then they represent constraints in the system. These constraints imposed on the motion of the bodies results in the fact that the accelerations of the cart and the weight have the same magnitude. By applying the fundamental equation of dynamics for the two bodies, we can state that the mass m1 of the weight times the magnitude of the acceleration A is equal to the mass m1 times the magnitude of the gravitational acceleration g, minus the magnitude of the force F'. Similarly, the mass m2 of the cart times the magnitude of the acceleration A is equal to the magnitude of the force F'. The sum of these two equations gives the equation stating that the sum of m1 and m2 times A is equal to m1 times g. If we divide this equation by the sum of m1 and m2, we can express the magnitude of the acceleration of the two bodies as the fraction of the mass m1 to the sum of the mass m1 and the mass m2, times the magnitude of the gravitational acceleration g. We can substitute this result into the fundamental equations, and express the magnitude of the constrained force F' as the mass m1 times the magnitude of the gravitational acceleration g, times the quantity of 1 minus the ratio of m1 to the sum of m1 and m2, or as the ratio of m1 times m2 to the sum of m1 and m2, times the magnitude of the gravitational acceleration g. For example, if the mass of the weight hanging from the spring is equal to 0.2 kg and the mass of the cart is equal to 0.8 kg, then the force F' measured in the system at rest is given by the mass m2, that is 0.8 kg times the gravitational acceleration, that is 9.81 meter per second squared, which is equal to 7.848 Newton. In the moving system, the acceleration A is equal to the gravitational acceleration g divided by 5, or 1.96 meter per second squared. The force F' accelerating the cart is given by 4/5, times the mass m1 times the gravitational acceleration g, which is equal to 6.278 Newton. This result also demonstrates that the force measured by the spring scale in the moving system is smaller than the one measured in the system at rest. As in the case of the experiment with the ramp, the measured acceleration of the cart is about 5 to 10% smaller than the computed value where the friction and the rotation of the wheels of the cart are neglected. Although the experiment shows that the acceleration is equal to the ratio of the force given by m1 times the gravitational acceleration g to the sum of the mass m1 and the mass m2, it cannot be used as an illustration of the second law of motion for a point mass m1 plus m2. We obtained this result in a system of two bodies and strings, which cannot be approximated as a single point mass. In the next example, we present the basic experiment with an Atwood machine shown in the illustration. The apparatus consists of a pulley attached to a stand with the masses connected by a string that runs over the pulley. A length scale and a pendulum are also mounted on the stand to measure the distance covered by the moving masses and the elapsed time, respectively. A small weight called rider is placed on one of the masses hanging from the string, where the string is pulled through a hole on the rider. Let us denote the total mass suspended in the right-hand side of the pulley and the mass of the weight hanging in the left-hand side by m1 and m2, respectively. In this setup, the mass m1 is greater than the mass m2, and the weights g1 and g2 acting on both sides of the pulley are not balanced. As a result, the net force acting on the masses will accelerate the bodies in the vertical direction. Since the weight and the rider have the total mass m1, the gravitational force g1 is equal to m1 times the gravitational acceleration g. Similarly, the gravitational force g2 is given by the mass m2 of the weight times the gravitational acceleration g. Then the magnitude of the net force acting on the weight and the ride is equal to the mass m1 times the magnitude of the gravitational acceleration g, minus the magnitude of the force F' exerted by the string. Similarly, the magnitude of the net force acting on the weight in the left-hand side is given by the magnitude of the force F' exerted by the string, minus the mass m2 times the magnitude of the gravitational acceleration g. Here we assume that the mass of the pulley can be neglected and the string cannot be stretched. Therefore, the forces exerted by the string at both ends have the same magnitude. These forces can be substituted into the fundamental equation of dynamics applied for the weights hanging from the string. Then we can state that the mass m1 times the magnitude of the acceleration a of the system is equal to the mass m1 times the magnitude of the gravitational acceleration g, minus the magnitude of the force F'. Similarly, we can state that the mass m2 times the magnitude of the acceleration a of the system is equal to the magnitude of the force F', minus the mass m2 times the magnitude of the gravitational acceleration g. The sum of these equations gives the equation stating that the sum of the masses m1 and m2 times the magnitude of the acceleration a is equal to the difference of the masses m1 and m2 times the gravitational acceleration g. We can express the magnitude of the acceleration a of the moving weights from this equation, as the ratio of the difference of the masses m1 and m2 to the sum of the masses m1 and m2, times the magnitude of the gravitational acceleration g. By substituting this result into the fundamental equations applied for the moving bodies, the magnitude of the constrained force F' can be written as the mass m1 times the magnitude of the gravitational acceleration g, times the quantity of 1 minus the ratio of the difference of the masses m1 and m2 to the sum of the masses m1 and m2. Or the mass m2 times the magnitude of the gravitational acceleration g, times the quantity of 1 plus the ratio of the difference of the masses m1 and m2 to the sum of the masses m1 and m2. If we insert spring scales in the vertical parts of the strings, then we can measure the constrained force F', which is less than the weight g1 and greater than the weight g2. With the vertical length scale and the pendulum, we can measure the distance s covered by the moving bodies during a given time t. It also allows us to demonstrate that the motion has a uniform acceleration by testing the distance formula, which states that the covered distance s of the accelerating bodies is equal to their acceleration a divided by 2, times the square of the measured time t. We can also show that the speed v of the bodies is equal to their acceleration a times the time t. When the weight with the rider is released, it accelerates for a distance s till the rider is caught by a ring allowing the weight to pass. From that moment, the weights g1 are the same in both sides, and so are the forces F' exerted by both the ends of the string. As a result, the net forces acting on the weights vanish, and the system moves at a constant speed v, which can be determined by measuring the elapsed time t' for the motion through the distance s'. Then the speed v of the bodies performing a uniform linear motion is equal to the ratio of the distance s' to the time t', and the acceleration a in the first stage of the motion is given by the ratio of the speed v to the time t. If we know the distance s, the acceleration a and the time t, we can verify the distance formula by substituting their values into the formula. We have seen that the right-hand weight of the Atwood machine is lowered and the left-hand weight is lifted while they were accelerated. Let us discuss this vertical acceleration of the masses suspended from the spring in both cases separately. We will consider a weight suspended from a string, where a spring scale is used to measure the force exerted on the mass by the string. First we lift a mass m with the acceleration a, as seen in the figure. Here the gravitational force g acting on the weight is given by the mass m times the gravitational acceleration g. If F denotes the force exerted on the mass by the string, then the net force acting on the body is equal to the vector sum of the force F and the weight g. We note that the acceleration of the mass points upward, that is, it has the same direction as the force F. Then the fundamental equation of dynamics applied for the body states that the mass m times the magnitude of the acceleration a is equal to the magnitude of the force F exerted on the body, minus the mass m times the magnitude of the gravitational acceleration g. Then we conclude that in order to lift a mass m with the acceleration a, we need to exert the force F on it, where the magnitude of the force is given by the mass m times the sum of the magnitudes of the gravitational acceleration g and the acceleration a of the body. That is, we exert a force on the body which is greater than the gravitational force acting on the body. In the second case, we study the lowering of the mass m with the acceleration a. Since the directions of the force F and the weight g acting on the body are the same as in the first case and the weight is accelerating downward, the acceleration a and the force F point in opposite directions. As a result, the fundamental equation of dynamics states that the mass m times the magnitude of the acceleration a is equal to the mass m times the magnitude of the gravitational acceleration g, minus the magnitude of the force F exerted on the body. Then the magnitude of the force F is given by the mass m times the difference between the magnitudes of the gravitational acceleration g and the acceleration a of the body. That is, we exert a force on the body which is smaller than the gravitational force acting on the body. In the case of uniform linear motion, the acceleration vanishes and the fundamental equation reduces the equation stating that the force exerted by the string on the body is equal to its mass m times the gravitational acceleration g. That is, the force F compensates the gravitational force and the net force exerted on the body vanishes. This phenomenon can also be demonstrated as follows. If we step on a body weighing machine and crouch down suddenly, then we decelerate our body downward, that is, we accelerate the mass of our body upward. As a result, the force F measured by the weighing machine is smaller than our weight given by the mass m of our body times the gravitational acceleration g. If we straighten while we are still standing on the weighing machine, then we accelerate our body downward, and the force F measured by the weighing machine is greater than our weight measured at rest. We will finish the series of examples presented here with another simple experiment where a stand is erected on the pan of a weighing scale, and a flywheel is suspended on it by winding a string around its axis. We can balance the mass m of the stand and the flywheel with some weight placed on the other pan of the scale. If the flywheel is completely wound up and held in that position, it will wind down after its release, and its acceleration a will point downward. As a result, the magnitude of the force F measured by the weighing scale is equal to the mass m times the difference of the magnitudes of the gravitational acceleration g and the acceleration a, which is smaller than the weight of the stand and the flywheel. When the flywheel has completely unwound all the string, it reverses the direction of its motion and starts to wind up, whereas its center has a decelerating motion upwards. That is, its acceleration a still points downward. Then the force F measured by the weighing scale is still the same, and its magnitude is equal to m times the difference of g and a. That is, the scale still measures a force smaller than the weight of the stand and the flywheel.